At the end of my first year of teaching, I just taught a year 4 class for the year. I received some gifts and presents and things from the parents, which I'm sure is very customary around the world. In amongst those presents was a book token, and at that stage of my career I thought the right thing to do would be to spend it on something that would help me in my own continuing professional development. And I bought this book, Speed Maths, which is all about shortcuts and things, and very much went against the way we were taught to teach at that stage. So the idea behind exploring any new concept of that age group was to start with something concrete. So you'd actually have physical representations of large quantities, this sort of thing. And it kind of makes sense. The idea is that you can kind of explore and see how numbers are really made up. So this is 3,201, for example, or, you know, another way, where's it gone? Another way might be with place value discs, where as well as just writing down the numbers, you could use a whiteboard or play with tokens or use manipulatives or even just visualize exactly what's going on inside of numbers. So here we've got 4,111. And it's all good to make sure the kids could see what's inside the numbers. But this book took a different approach. It was full of tricks, and it wasn't, the emphasis is not on understanding what's happening, but just remembering a bunch of tricks. And I was quite taken by it. And it, you know, some tricks would work like this. So for example, you want to multiply two large numbers, let's say 80 times 91. So there are various formal column methods you could use to do this, but Bill Handley had this idea, this little trick that you would use a reference number. So say 100. 100 is a nice easy number to work with, and then you'd find the difference each number was away from that base number. And then the party trick was this, to swap the numbers around, then apply it to the number above. So 80 take away 9 is 71. 91 take away 20 is 71, and that gives you the first part of the number. And then, interestingly, you would then take the two differences, multiply them together, and then you would add that on. And the idea is that you would do this all mentally. And 80 times 91 is a bit interesting. It's a bit tricky. I don't know what method you would naturally take for this. I'm not sure what I would do. I don't know. Would I go 10 times 91 and then multiply that by 8? I'm not sure. But it's not always great. But I thought it was quite interesting. And so, you know, later on, now here we are where everyone's vibe coding. I thought I'd have a go at creating this visualization to show this process. And for some numbers, you know, it feels quite sweet. It's quite nice to work with. So if we are very close to 100, so let's do 98 times, I don't know, 97. Then suddenly it becomes like quite a nifty trick. We find the differences, we cross them over, we apply to the number above. And so we have 98 take away 3 and 97 take away 2, both giving us 95. And then you multiply the differences and add it on to the end. And like that feels like something I could cope with, and, you know, maybe I'd consider doing. I'm not sure how far I'd be able to continue doing that with smaller numbers. And then, you know, a couple of other examples. It'd work if the number is above. So if I have 106 and I want to multiply that by 98, we pick a base. I mean, it's very close to 100 still. And this time we have a positive and a negative. We swap them over and apply it to the number above. So 106 take away 2, and 98 plus 6 gives us 104. We multiply the differences together to get negative 12. And then we have this situation where we have to subtract 12 from 10,400. And there you go, 10,388. And I do find this quite interesting. However, I mean, I think the mental effort required in trying to remember this process, and especially the further you get away from the base. So let's do something awkward. So if I do 78 and then, I don't know, 72, suddenly, okay, here we're using 50 as a base. So I'm going to reset that. I'll come back to using 50 as a base in a moment. But let's stick to slightly more awkward numbers. So 83 times, let's try it, times 79. Okay, so here we have 100 as a base again. And we have much bigger differences. And then we can do the maths in the usual way by applying to the number above. So this bit is not so taxing. But I find it quite interesting with Bill Handley's method that the idea is now mentally you would then do negative 21 times negative 17. So multiply those two numbers together. And in my head, you'd then need to do a sort of separate calculation using 20 as a base. And I think it's at that point, I think the faff factor kicks in. But it's still a nice idea. There we go. But you don't have to use 100 as a base. Obviously, 100 is great. But if we do pick a number that's closer to 50, say, then we have this situation where we use 50 as a base. We do the same thing to begin with. So 45 plus 1 or 51 take away 5, both give us 56. But then we have to remember that because 50 is half of 100, we then need to halve that number too. So we have 23, and then the same thing applies. 1 times 5, negative 5. So we have 2,300 take away 5, gives us 2,295. Fine. I just don't know, would you use this method in your head? I don't know, but I do find it interesting. I mean, I like it when you take a number using this concept. So take 8 times 7, right? We all know this is 56, but if we just work through the steps using 10 as a base, I do find it quite interesting. So 8 take away 2, 7 take away 3, swap them over, apply to the number above. So we have a 5. Well, we know we're going towards 56. But then we do negative 3 times negative 2, ending up with 6. I mean, I don't know what I would do if a kid in my class actually wrote that down as their formal method. I do like it though. I do think it's quite fun. It's a nifty party trick. So maybe we could try it with something a bit more awkward. So let's try and stick to using 10 as a base. So I'll do 14 times 8. You know, hopefully this jumps out to you. I think, what would I do here? I mean, I think I'd do, 10 times 8 and then 10 times 4 and then add those two answers together. But I thought, would this be quicker? So the difference between the number and the base, we've got a 4 and a 2. We swap them over. We apply to the number above, 12. And then we do negative 2 times 4, which gives us a negative number, negative 8. So 120, take away that 8, gives us 112. I don't know. I do like it, but I think there's a few steps where, I would, if you're just trying to memorize a little routine, I think there's a few steps where I could go quite easily wrong here. What about if we go super awkward? So let's see if we try with a more awkward number. So if we take 13, which is close to 10, and then if we do 35, and what will we get here? Which base do we use? Right, so we use 20, okay? So fine, so we find the differences. 13 take away 7, and 35 plus 15. Either way, we swap them over, and then we end up with 28 by applying to the number above. But here's the step where it might be a bit confusing. So what do we do with that? Do we divide it by 5 because 20 goes into 100 5 times? Actually, we have to consider its relationship to 10, in which case we double it. So 28 times 2, 56. And then we multiply the differences, negative 105. And now we have to remember that 56 is actually 560. Take away 105. Which gives us 455. Okay, fine. I'm not convinced that this method is even mentally going to be any more better. I think we do a better job of compartmentalizing 10 times 35 and 3 times 35 and then adding them together. But sure, fine. I did like these methods. I have had fun coding them, this little application, which you can, I'll put a link to it in the description so you can have a little play with too. But yeah, one more. Let's do 51. Let's square a number. 51 times 51. We use 50 as a base. Swap them over. We add 1 to each. So we have 52. We divide that by 2 because it's half of 100. And then we have 1 times 1, 1. We bolt that onto the end, 2,601. Would that ever come in handy? I don't know. The idea behind these methods is that you can do them quicker than a calculator, right? Fine. So 95 times 95, just maybe if it's a nice friendly number like this, I would consider trying to memorize this, because this is quite nice, isn't it? 90, then we do 5 times 5 and bolt on 25 at the end. Yeah. Personally, I think kids, new learners, are still better off learning to partition the number in their mind between multiplying by the number by 10 and then multiplying the number by the units as well. Anyway, what do you think? If you want, you can click the link in the description and you can have a little play on my site. Let me know what you think of these sort of methods. 7 times 5, let's do it the ridiculous way. But 10 as a base, -3, and -5, swap them over, apply to the number above. I mean, even though I know the answer, I feel like, where's it going? Oh, 35. Let's do one more ridiculous one, okay? What about 1 times 1 using this method, right? 1 times 1, so we know where we're going with this. This is almost farcical now. -9, swap them over. Right, now we've got -8. And now we square -9 to get 81. And then we add those two together. I love that. Ridiculous, but I love it. Anyway, let me know what you think.